My computer is telling me that I don't have an internet connection. However, you've just heard me and I've just heard you, so I think we will get started soon. Lovely to see you, Dr. Noor. It's wonderful to hear about your latest research. It's exactly 2 o'clock, so I know you've got plenty to tell us about. So without further ado, I'd like to welcome everyone who's joining us for this research seminar. Thank you very much for everyone who's been coming every 2 weeks regularly and faithfully supporting the research culture at the School of Arts and Sciences. We often have internal and external colleagues attending these seminars. I believe today's research is quite different to what we have been used to. This is pure mathematical research, which I'm really looking forward to hearing. It's hot off the press, it's innovative and original. So thank you so much for joining us today. Dr. Noors, over to you.
Okay, thank you, Dean Jnainati. So first, I would like to thank the organizers to give me this opportunity, and I will thank all the attendees for attending this talk. So this is a joint work with the Professor Vera Zaidan from Michigan State University. So I began to work with the Professor Zaidan, let's say 3 years ago. And we were very productive in these 3 years. At least we have something positive from Corona, staying at home and working all the days. So it is really a big honor for me to work with such a big name in her field, and I would like to thank her for working with me. So as you can see, the title of the talk is the numerical solution for a controlled non-convex sweeping process. So you can directly deduce from the title that this is an applied talk, so applied mathematics, which is not my research field and not the research field even of Professor Zaidan. So it was something new for us to see how our theoretical result can be applied in real life problems, and it was a very nice experience for us. So the outline of the talk is the following. So first, I will give you, I'll state the problem on which we will work. I will talk a little bit about its very special dynamic. In the second part, I will present the previous results done for this kind of problems. I will explain why they have some restrictions on the set C and the point x0. You will understand this in a few minutes. And then I will explain in the third part how we overcome these difficulties and we succeed to take general initial points x0 and non-convex set C. And at the end, I will give an example, numerical example, in which I will show you how we can solve the problem numerically and obtain not only the minimum value of the problem, we also obtain the solution, the optimal trajectory solution of the problem. So we will work with this problem. This is a optimal control problem. The dynamic is bit dynamic D. You can see that this is a differential inclusion. So we have x dot belongs to fx du minus the normal cone. Now, of course, if you don't have this part, which is the normal cone part, then you have a ordinary and well-known standard optimal control problem. So for concerning the data of the problem P, you have G, the function from Rn to R. This is the cost function. You have f from Rn cross Rm to Rn, which is the dynamic function. The set C is the set of all x such that C of x is less or equals than 0, which means that C is the sublevel set of a function psi. You have NC is the Clark normal cone. We call this Clark normal cone. Let me mention that Clark is my PhD supervisor, and he is also the supervisor of Professor Vera Zaidan. Okay, so she is the first student, and I think I am the last one or the before last one student this professor. So the x0 is the initial point. It's a fixed point in the set C. And script U, it will be the set of all measurable control functions. So let me talk a little bit about what's the meaning of XU admissible. When we say that the pair XU is admissible, of course, if it satisfies the condition of the dynamic D, plus that the function U, it must be, of course, in script U. And what's the meaning of optimal solution? And this is what this is our goal, to find this optimal solution. So we need to find X bar U bar, which is admissible for the problem P, and of course we need that the cost function at X bar of T, it must be less than G of X T for any XU admissible. Now I will talk a little bit about the dynamic D, which is very special for this problem. So if you see the dynamic, there is something special, which is the existence of a normal cone. So this kind of dynamic is called Sweepring process. It is introduced by Moreau in 1970s in the context of plasticity and friction theory. It has a lot of application in several fields like mechanics and so crowd motion problems, etc. Why this dynamic is very special? This is very special for the existence of the normal cone. Why? Because when you have the normal cone, you lose the boundedness of the right-hand side, and you lose the continuity of the right-hand side, because the normal cone is unbounded and the normal cone is discontinuous. And then you cannot now apply what we have already for a standard control problems, and then we need to create new methods. Okay, so this is the big problem for the dynamic D. Now, in the paper one done by Pinho, Ferreira, and Smirnov in 2020, they propose a numerical method to solve this optimal control problem. But if you see, they have two constraints on the initial condition x0 and the function psi, which is defining the set C. The first constraint is that x0, it must be inside the interior of the set C. And the second is the function psi must be convex and C2. So convex, it's a huge assumption, and you all know what that there is a big difference between working with functions convex and working with functions that are not convex. So these are the assumptions assumed by these authors. All the assumptions are, let's say, assumptions are standard, except that we have the convexity of the function psi, which means that the set C is convex, and we also have that x0 here is inside the interior. Now, having psi C2, we directly deduce that the normal cone is equals to this. So if you have a point on the boundary of C, it will be a scalar lambda positive times the gradient of the function. Inside the interior, it must be 0, and outside it is not defined. And now you can see why this set is unbounded, because here you are multiplying by lambda for any lambda, and you have the gradient at the boundary is different than 0. Why? Because you can see here that on the boundary you have the norm of the gradient is bigger than 2 eta, and then this set is unbounded. And we can add also that we don't have continuity. You can see that if you are in the interior, you have singleton 0, and once you go and you are on the boundary, directly you have now a set which is not 0 and not even bounded. Now, the method used in the paper 1, it was the following. It was a very genius idea, because they replaced the term, this normal cone here in the dynamic, they replace it by a term which is gamma e gamma psi x of t gradient of psi x of t. And of course, gamma, it must go to infinity when k goes to infinity. And then the dynamic d gamma k, we call this approximating dynamic. It will be x dot equal u minus this term. And then now you can see that the dynamic d gamma k, it's a ordinary a differential equation, and then you have a ordinary or standard control problem. So they define now the problem P gamma K, which is the same problem like P, but you replace the dynamic D gamma D by the dynamic approximating dynamic D gamma K. So now we have a ordinary standard optimal control problem. Now they begin to transform the problem from being a optimization problem, infinite optimization problem, to be an optimization problem finite dimension. Why? Because they will restrict the choice of the control to be only piecewise constant control. And this is done by taking any positive number, taking h equals to t divided by n, and then now P gamma K will restrict the study on the set of piecewise constant control. So we call this problem P and gamma K. And if you have a solution for this problem, it will be denoted by x hat and gamma K, u hat and gamma K. So this is the first theoretical result proved by these authors. They proved that for any epsilon, you can find K large, which means that gamma K is large, n large, in such a way that the value of the problem P and gamma K, it is very close to the value of the problem P, which is excellent. And they also succeed to prove that if you take the optimal solution of the problem P and gamma K, which is x hat gamma K, and you take K goes to infinity, n goes to infinity, this solution will converge uniformly to the optimal solution of P, which means now that if you can solve the problem P and gamma K, which I repeat, it's now a finite dimensional optimal control problem, then you're not only estimating the value of P, you are also finding a trajectory which is very close to the optimal trajectory of the problem P. So now let me explain to you quickly why they have these two restrictions. The first one, that the x0, the initial condition, it must be inside the interior of the set. And second, why they need to assume the convexity of the set C. Now, if you see the proof done by these authors, you will remark they need the uniform boundedness of the function gamma k e gamma k psi. And to have this, they need to have that the psi of the initial condition, it's always less or equal than minus alpha gamma k, which means that y0, it must be in the interior of the set C. And because d gamma k is approximating d, they must take x0 equals to y0, and then x0, it must be in the interior of the set C. Okay, so second, why they need the convexity? Because if you see the proof, they need the function e gamma k psi to be a convex function, because they need this inequality in their proof. And to be honest, they need this inequality only on the solution of d gamma k, not everywhere. So the big question is now how we can have the same result by not assuming that the initial condition is inside the interior of the set, and by not assuming the convexity. So let me explain first how we can answer to the first question, which is eliminating x0 from being inside the interior of the set. So we introduce these two sequences. The first one is alpha k. It's ln n eta gamma k divided by 2m divided by gamma k. So eta, you remember this is the condition on the gradient of the function psi. Gamma k is the sequence that converges to infinity. M, it's an upper bound for the function f, the dynamic function. And we define rho k to be alpha k divided by eta. So we also define the set C gamma k, which is a subset of C, and it is the negative alpha k sublevel set of C. You can see that C gamma k, it's not only a subset of C, it is a subset of the interior of C. And its Pon-Level limit is equal to the set C. Now we define this sequence. So you can see if the point x0 is inside the interior, then we define the sequence to be the constant sequence x0. But now, if the point x0 is on the boundary of C, now we create a sequence inside the interior, which is x0 minus rho k gradient of C at x0 divided by norm gradient of C at x0. And this sequence is inside now the interior, and it converges to the point x0. And then we have the following lemma. Of course, k0 converges to x0 when k goes to infinity. This is very easy. Why? Because rho k, it converges to 0 when k goes to infinity, because alpha k converges to 0. And we have that xk, it's always inside ck, which means that it is inside the interior. And what is very important, that for this xk0, if you take the solution x gamma k that of d gamma k that begins from this xk0, you have the uniform boundedness of gamma k e gamma k psi. And moreover, you have also that x gamma k will remain inside the set C of k, which means that x gamma k will remain inside the interior of the set. I need to say something important about maybe someone will say, okay, it's not a big idea, because okay, when you are on the boundary, you can take any sequence inside the interior that converges to x0 and then work using the previous results, work on this sequence. The answer is no. We want this sequence. Why? Because this sequence is not only converging to x0 from the interior, it is also giving me that gamma k e gamma k psi is uniformly bounded. And if you remember, we need this here, the uniform boundedness of this sequence. So this sequence is needed, this alpha k is needed, and this rho k is needed to create this sequence. Okay, now we move to explain how we can eliminate the convexity of the set C. Let me recall that the convexity is needed for this inequality. Okay, because when you have psi convex, you have e gamma k psi is convex, and then you have directly that this inner product, it's always bigger or equals than 0. So to do this, we have the following lemma. We prove the following lemma. For any n bigger than 1, if you assume that the boundary of C is connected, which is a very weak assumption if you compare it with the convexity of the set C, then you can find a constant m bar such that this inequality, it's very close to the old inequality where you have greater or equals than 0, but now you have greater or equals than minus m bar norm y minus x squared. And thanks God, it's enough for us to prove the same results done by Pinho, Ferreira, and Smirnov to do exactly the same with this inequality. And then this is our algorithm to solve the problem P now. So we fix n large at the beginning, epsilon small, gamma k, and delta. So gamma k, it is the initial value of the sequence gamma k, and delta is by how much we increment for each iteration the sequence gamma k. So the idea is the following. First, for fixed k, we compute the value of the sequence xk0. We solve the problem Pn gamma k for initial condition xi0. So we take the value g at the end point of this solution xn gamma k hat. And then once we obtain gk and gk plus 1, the difference less than epsilon, then we will stop, and then we have the answer. Now, let me move to a numerical example, because here there are a lot of things that I need to clarify. For example, compute a solution for P and gamma k. It's not something very easy. I need to explain how we will do this. Okay, so this is a numerical example. I will take mn equals to 2. The time, it will be pi. The set u, which must be compact, it's the interval -4, 3 cross 0, 7. So the dynamic function f is given by xu minus y for the first component, yv plus x for the second. The cost function g is given by 5x squared minus 4y squared plus 6. What is important for us is the function psi, which is a function not convex. And if you sketch the level set of this function, you obtain a well-known set called Cassini oval, which is not convex. As you can see here, you have non-convexity. Now, for the initial condition, we take the point to be on the boundary because we want to show in this example that our algorithm is working when you have a point on the boundary and you have the set C not convex. So the function G, it's very easy to prove that the function G, it has a global minimum at 0, 1 and 0, minus 1, here and here. And then you can conclude now, if you have a solution for the dynamic D that ends at 0, 1 or at 0, minus 1, then it must be, of course, an optimal solution for the problem P. Okay, and in that case, the minimum value of the problem P, it will be the value of G at 0, 1 or 0, minus 1, and it is exactly equals to 2. So now let me write for you the problem P and gamma K that I defined a few minutes ago. So it's the same problem like a P, but now we work on piecewise continuous control, which means that we have a finite dimensional optimization problem. And we replace the dynamic D by the dynamic D gamma K. So this is the formula for the dynamic D gamma K. As you can see, the initial condition now is radical 5 minus ln gamma K minus ln phi divided by 6 gamma K 0. This is the sequence that I defined a few minutes ago, which is x gamma K 0. So now the question is how we can solve this problem numerically. So we choose n equals to 25. Gamma equals to 10, and we will increment gamma by 10 for each iteration. And for epsilon, I will take it 3 values, and I will show you the answer for each value, 0.1, 0.01, and 0.001. Now, let me explain to you what numerical method we need to use to apply our algorithm. So I will define for you a function. I will call it gk. So imagine now k is fixed. So you are fixing the iteration. What you need to do for a given control u1 v1 till u1 25 v25, which means that I'm choosing a point inside this compact set that I defined a few minutes ago, this minus 43 cross 07. So if you take a choice for such a control, you compute the initial condition because you have a formula, it's easy. And now you need to compute numerically the solution of the dynamic D25 gamma K for the initial condition xk0, yk0, and for the control that you choose at the beginning. So the question is how I can compute this numerically, this solution, because you have a ordinary differential equation and you want to solve it. So we will use a well-known method, Runge-Kutta method of order 4. We will use a step size of 0.0001 on each interval 20, on each of the 25 intervals. Now, once you find the solution numerically, you take the end point of the solution and you compute the value of the cost at this point. So now this is one iteration. What we need to do to solve the problem and find the answer, we need to minimize this function gk, capital GK. We need to minimize it on the set of point uv that you choose 25 a point inside the compact set minus 43 cross 07. So now you see that this is really a optimization problem, finite dimension, because the set of points uv are 25 points inside the compact set. But what is something very special for this problem is that this function gk, you don't have it explicitly, you have it only numerically. And now the question, how I find the minimum of a function that I have it only numerically. So this is what we call in applied math the derivative-free optimization. So when you want to minimize the function, but you only have the function numerically, so we need to use what we call derivative-free optimization, because you don't have a formula for the function to use a well-known method that uses the derivative of the function. And let me say something here important concerning this work. So when we published this work in the IEEE journal, we asked Dr. Khatib to help us to create a method to solve this optimization problem. So rank quota is something, it exists, so it's known and you have it on MATLAB, it's very easy. But for this kind of problems, which method we will use? So we asked Dr. Khatib to help us. So he created a method, call it, I think, mesh minimization technique. And using this method, we succeed to reach the optimal solution and the optimal value. But after that, and after the acceptance of the paper, I asked of one of my students in our master here at LEU to help me to find another method, more theoretical method that solves this kind of problems. And I will thank my student Jean Zigondi because he helped me to write a code to solve this problem using what we call a well-known method, the Nelder-Mead derivative-free optimization method. So let me show you the results and discuss these results. So we use MATLAB for Nelder-Mead, and we use it also for a Runge-Kutta method of order 4. So we apply first the algorithm for epsilon equals to 0.1. So the program will terminate after only 2 iterations, which means that gamma, it will be 30, because 10, 20, 30. So the value of G, it was 2.09. So it's very close to 2, that we believe it will be the optimal value if there is a solution that will end at 0, 1 or at 0, -1. And what is nice that we obtain this trajectory. So you see the trajectory, it begins very close to radical 5, 0. It terminates at 0, 1. Then we decrement epsilon, we divide it by 10, and then we obtain 4 iterations, which means that gamma k will reach the 50. And the value of G now is 2.07. And you obtain a trajectory which is very close to the boundary of the Cassini oval. So now we decrement epsilon, it is now 0.001. So now you see we must do 21 iterations. So gamma, which now it's very large, it's 220. And the value of G is 2.02. And you see that the trajectory is completely on the boundary of the Cassini oval. And then now we not only have the minimum, which is 2, we also have a trajectory which is optimal for the problem P. It is the boundary of the Cassini oval. And then it was very challenging for us, for me and for Professor Zaidan. We want to prove that really this is the solution analytically. So we want to prove that we can find a control for which we can solve the dynamic D for this control and obtain this trajectory. And it was very challenging for us. Let me explain why. Someone will tell me why. You only need to take the parameterization of the Cassini oval, which is known. The answer is we cannot do this. Why? Because if you take the parameterization of the Cassini oval, because we are working on the interval 0 pi, the trajectory will end here at negative radical 5, 0. So it's not a good idea to take the parameterization of the Cassini oval because it will not be a solution for the dynamic D. And we work for about, I think I remember, for about 1 hour discussion how we will prove it analytically, because it was very challenging for us. We have the solution numerically, but we want to prove it really that it is the solution. And we succeed to find a control and to prove that this is a solution, but by a very nice idea. The idea is the following. As I said, if you take the parameterization of the Cassini oval, you will end at the point minus radical 5, 0. And then the idea is the following. We will move from radical 5, 0 for a time of pi over 4. So we'll be here. And then we will stop here for a certain time, which is interval pi over 4, 3 pi over 4. We will stop at the point, so which means that x dot, y dot is now 0. And then we continue to be exactly at 0.1. So the idea is to stop, okay? And we succeed to prove that this is a solution for the dynamic D, which means that we need to find a control, and we need to find also, if you remember, the lambda in the definition of the normal cone. So each time you want to prove that a trajectory is a solution, you need to find the control, and you need to find also the lambda that is multiplying the gradient of the function psi, because as you can see, the trajectory is on the boundary, which means that the normal cone here is not 0. It is lambda times the gradient of the point at the point of psi. And then we proved analytically that this is really a solution. And then, yes, the optimal value is equals to 2. And this is what we obtain, what we have obtained numerically. So what is nice in this example that we have the numerical method help us to find not only the minimal value, the optimal value, but even the trajectory, and this will push you, of course, to prove it analytically that this is a solution. Now, maybe someone will ask me, what about the control that you obtain? It is the optimal control also? The answer, of course, is no. Why? Because the control that you obtain numerical, it will be a piecewise constant control. But the control of the dynamic or the problem P, it's a continuous function. So let me say something important, that we didn't try this algorithm on a problem that the solution of the problem P, it is a piecewise constant control. And what is nice, that what we obtain numerically is exactly this piecewise constant control, which means that this algorithm will give you, if your solution is a piecewise constant, it will give you also exactly the control. So if not, then you obtain something close, let's say, to the control, but it is a piecewise constant control, not a continuous function. Okay, so these are the references linked to this work. Let me say something important. Why we did this work? Because for the problem at P, Pinho, Ferreira, and Smirnov did find what we call a maximum principle for this kind of problems, and they found this only for the convex case, and for C being C2 and F being C11, etc. So what we did with Professor Zaidan and also with Dr. Saoud, first is generalize this maximum principle for the convex case and for the case in which the data is not necessarily smooth. And then once the Pinho, Ferreira, Smirnov did a numerical solution for the problem in the convex case and in the case where x0 inside the interior, of course, naturally, we directly generalize this result also to the non-convex case. Okay, thank you very much for your attention.
Thank you so much for this wonderfully detailed talk, Dr. Noor. Thank you for the very because I was really and absorb myself into your research. So we will open the floor for any questions. Please feel free to unmute and ask a question, or raise your hand, or just put the question in the chat. Dr. Isa, go ahead, please.
Hi. Sorry, I would like noise. I have to hide from my children to be able to unmute myself. Anyway, thank you, Shadi, for this nice presentation. I have a question on how sensitive is the method to the choice of the numerical method to solve the ODE? Yani, had you chosen something other than RK4? And the reason I'm asking this, and maybe correct me if I'm wrong, but each time you run the optimization, you have to run many RK4s, right?
Yes, of course. Yes.
So if you could afford a cheapest method, maybe that would be less complex computation-wise. That's why I'm asking.
I think that Jean Zigondi, my student, tried to use another method, less powerful than range quota 4, but range quota 4 it was much better. So you reach let's say with less iteration. I agree with you that it will take more time because you have range quota 4 and you know it's complicated. But small, less iteration, you will reach the solution. Faster, of course, it's better if you use less powerful one. But let me say something important about the solution of the differential equation here, because there is something very important inside the differential equation of d gamma k. And this is creating a problem for us. Now, we are working on that, on the numerical part. If you see this C gamma k, you see that it is gamma k, and you have E gamma k times this psi, which is the value of psi. And you know that with psi, it's always less or equals than 0 when you are inside the set C. And then if psi is very negative, which means that, let's say, minus 2 point something, and gamma k becomes very large, we will have a problem because
it's stiff,
will explode. Yes, بيصير explode يعني range quota بتقول
so
okay, I will stop.
It's a stiff ODE. I think you would want something to deal with stiff ODEs.
Exactly. We are working on that now to see how we will manage with this, because and this will happen always when you are not close to the boundary, because if you are close to the boundary, your psi is close to 0, and then this term, the exponential term, will not explode. But if you are not very close to the boundary, let's say in the middle of the set C, your psi is very small. You have minus 4 times gamma k, which is, let's say, 200, then we have a problem. So we are working on this part to see how we can manage to not have the program telling us, okay, I cannot continue.
Okay, thanks, Shad. Thanks.
Thank you for your question. I noticed that your collaborator, Dr. Zaidan, is with us. Welcome, Dr. Zaidan. It's lovely to meet you virtually. Are there any other questions for Dr. Noor? I'm sorry, this is really not my field, Dr. Noor, so I really cannot entertain a question. Okay, I don't see any hands raised. Please, if you can't raise your hand, but you wish to ask a question, just go ahead and unmute yourself. All right. Thank you. All the best with this exceptional research that you're conducting with your collaborators. And we look forward to learning about the various publications that ensue. Thank you so much for joining us today and for sharing your research with us. Thank you to everyone who attended. Please come back. It's every fortnight. We have research seminars in every single field that we have at the School of Arts and Sciences. Thank you for switching your camera on, Dr. Zaidan. It's lovely to see you.
I have difficulties unmuting myself, so thank you so much for your comment.
Of course. Let's see. I can see something in the chat now. Yes, thank you for sharing your email address, Dr. Noor, in case anyone wishes to pursue some more complicated and intellectual questions with you. Thank you, everyone. Hope to see you in a fortnight, same time, same place. Goodbye for now. Enjoy a warm and cozy weekend. Goodbye for now. Bye, Dr. Noor.
Thank you. Thank you. Bye.